So, what we've been looking at so far when we talk about aldol additions are self-aldol additions, where we have a single aldehyde or ketone, and the nucleophilic enolate anion is derived from that same aldehyde or ketone. So basically, a molecule that reacts with itself. Okay. Now, so maybe the burning question in your heart is, hey, Dr. Pierce, can we have a molecule react with another molecule, right? That's different. And the answer is yes. And that's called a crossed aldol addition. And in a crossed aldol addition, a nucleophilic enolate anion is generated from a different aldehyde or ketone than the one that's attacked. And an example is shown here in 1941, where we have the enolate anion of propanol attacking an uncharged molecule of ethanol, which is also known as acetaldehyde, yielding 3-hydroxy 2-methyl-butanol. Okay, so we can see that that's a crossed aldehyde. But one of the things that is unfortunate about this is you just don't get the desired product here. You can get a lot of different products. So, for example, if we look here, right, we've got propanol, we've got ethanol, and while we're trying to get this, right, there are also 3 other aldol products that we can get as well. And so let's look at kind of how that happens. So what we see here is that propanol can react with propanol, right, and do a self-aldol. It can also react for a crossed aldol, right, and so we can react here and here. Then ethanol, right, can react in a self-aldol as well as a crossed aldol. So these 3 other aldol products, they lower the yield, and they're also really difficult to separate. So when we have a reaction like this, we have a lower yield, and they're difficult to separate from each other because they're just going to have similar physical properties. So this kind of reaction isn't super useful, which is unfortunate. Now, that doesn't mean that all crossed aldol reactions aren't useful. One way kind of around this is to use an aldehyde that has no alpha hydrogens, like methanol, right? Or benzaldehyde or dimethylpropanol. So if an aldehyde with alpha hydrogens is slowly added to a basic solution, right, of an aldehyde without alpha hydrogens, one primary aldol product is formed, okay? And this here we're forming cinnamaldehyde, which is one of the molecules found in cinnamon. It gives it its characteristic flavor and odor. And so it's the principal component of that essential oil from cinnamon bark. But we only get one aldol here, and that's because benzaldehyde has no alpha hydrogens. So it can't be deprotonated by the NaOH and doesn't form an enolate ion, right? And so we also we add it slowly so it'll avoid the buildup of an uncharged aldehyde as well. So there's some workarounds around this. So let's look at a problem, okay? So we're going to predict the product of the reaction shown here where propanol is added slowly to a basic solution of formaldehyde. And we want to ask ourselves some questions when we do this, right? Like, which aldehyde can form an enolate anion and which cannot? And so to do this, you need to look for alpha hydrogens, right? And so we see here that formaldehyde has no alpha hydrogens, right? So it can't form an enolate ion. Right? So that means that ethanol is the only one that can form an enolate ion. Okay. Sorry, propanal. 1, 2, 3. Propanal is the only one that can form an enolate ion. And so then the next question says, which uncharged aldehyde is present only in small concentrations in the reaction mixture? Well, if we add propanal slowly, there's never going to be a substantial concentration of its uncharged form. So the major reaction occurs between the propanol enolate ion and the formaldehyde. And this helps us, if we're adding the propanal slowly, not get any buildup of the propanal enolate anion, so we don't get the aldol product where propanal reacts with itself, basically. Okay, and so that's why we're adding things slowly. And then what impact does heat have on the outcome of the reaction? Because we're heating it, right? That's what the delta's for. Because it's heated, right, that's going to result in dehydration, which is going to lead to that condensation product, which is going to follow the E1CB mechanism, okay? And so when we look at this mechanism, and I know it says predict the product here, right? But I have a really hard time predicting the product without the mechanism. So we are going to do the mechanism, right? When we look at the mechanism here, right? These electrons are going to come down. They're going to steal that proton. These electrons are going to go back up on that carbon, right? So that means that now we have our enolate ion that we're adding all this really slowly. We've got our enolate ion. It's going to react here. So these electrons are going to come down. They're going to attack that carbonyl carbon. Those electrons are going to pop up there. Right? And now we have our aldol product, right? And then what we're going to see here, right, is that E1CB, and we're going to get the loss of H2O, the E1CB mechanism, and we are going to get dehydration. Right, and there's our condensation product, except I got real excited and added a second oxygen because the oxygen's lost through the water. So there we are. So there's our product. All right. Now, there's a couple different ways that we can carry out an aldol reaction. A second way to do this is to use a really strong base like lithium diisopropylamide, which is LDA, the structure of which is shown there, to generate the enolate anion. And this is shown in equation 1945. Now, this guy here is a very strong base, right? And so because of this, it's going to deprotonate that alpha carbon really rapidly, right? And irreversibly. And also quantitatively, it means it does it very well, right? There's a lot that's going on here. So basically what happens is essentially 100% of that cyclohexanone is converted to its enolate anion before the addition of the second carbonyl containing compound. So because it happens so fast, there's only one enolate anion available to react in the second step of the synthesis. And so you put cyclohexane in a flask, you add an LDA, it reacts very fast. Then you add in your enolate, your second carbonyl containing compound, which is shown here red. And so this is a kind of a better way to do this crossed aldol reaction, is to use LDA. Now, in aldol reactions involving ketones, regiochemistry does become a concern when the ketone has two chemically distinct alpha carbons. And so an example here is shown with methylbutanone right? There's a CH3 here, and then there would just be a CH here with the two R groups. And so what happens here is the alpha carbon that's deprotonated leads to one of two enolate anions, right? Which result in one of two aldol products, right? So we can have two different aldol products here. And of course, that can be a problem. But as we've learned, right, the choice of base can often control which enolate ion is predominantly formed, and that allows us to control the regiochemistry of these kind of aldol reactions. So let's look here at example 1947. It shows that NaOH is the base, and what we find here is when NaOH is the base, deprotonation is favored at the more substituted alpha carbon here, and the major aldol product has the form that appears right here. If LDA is used as the base, then deprotonation is favored here at the less substituted alpha carbon, and the major aldol product is here. You need to star this. We are going to do some problems like this, but it's something you really need to watch. You really need to pay attention if you're using NaOH or LDA, because they have different deprotonation sites, and that affects which product you're going to get here. Okay? Now, sometimes we have molecules that maybe have two functional groups, like two carbonyl groups. And so we may ask ourselves then, hey, Dr. Pierce, if we have a molecule that's got two carbonyl functional groups, could one functional group on one side of the molecule react with the other functional group on the other side of the molecule to give us a cyclic molecule? And the answer would be yes. Of course that can happen, right? So what we're looking at here is hexane diol. Now hexane diol has two carbonyl groups, and so what can happen is an intramolecular aldol reaction can happen where one part of the molecule reacts with the other part of the molecule, forming a ring. The mechanism for this reaction, we're going to do this on the next slide, but it's identical to the mechanism for an aldol condensation that occurs between two separate molecules. But I always like to look at it just, because sometimes this is harder to visualize. So let's work and do this mechanism. So we've added our base. That's going to give us this OH minus, right? And the first reaction we're going to have here is a proton transfer, right? And these electrons are going to come down and they're going to grab that proton, and those electrons are going to go back on that carbon. Okay? And so now we have formed this sucker here, this enolate anion, and it is resonance stabilized, and you can draw the resonance structure for that. And what we have here are these electrons are going to come around, right, and react with this carbonyl carbon. It's going to wrap around and make a ring. Okay, so that's going to be a nucleophilic addition. Reaction. And so what we see here is that product there. Then it's going to undergo a proton transfer with water, right? Where these electrons are going to come, they're going to grab that, and those electrons are going to go on there. And we've got that guy. Now, it's still pretty basic. So what we have happening here is this OH is going to come in and it's going to steal that hydrogen through a proton transfer. right? And those electrons are going to go right there on that carbon. Okay. And, ooh, I said they're going to go right there on that carbon. No, they are not going to go right there on that carbon. They're going to go there and form a double bond. So it goes right like this. It goes there. We go up. We have a hydrogen. We steal those. Sorry about that. They're going to go right there and form that double bond. And then that's going to pop off that OH through a heterolysis. Nope, I've skipped a proton transfer. I was right at the beginning. If I was better at editing, we would just edit over all that. I apologize. All right, sorry. I skipped a proton transfer. So yes, I was on the right track at the beginning. We have a proton transfer. So it goes proton transfer, nucleophilic addition, proton transfer, and then heterolysis. So let me draw this product. All right, now we're going to have the heterolysis, right, where these electrons come down here to form a double bond, and then that bumps off this OH molecule here. And when that happens, we end up with that guy right there. All right, now, not every molecule that has two functional groups will go together and form a ring, right? Because we do have this idea of ring strain. So cyclization reactions are generally favored when the product is a 5 or 6 membered ring. So, and these aldols are no different. Like, for example, you're not going to get pentane diol. That's a 4-membered ring. There's too much ring strain. You're not going to get that. A 7-member ring is not favorable. 5 or 6-membered rings are really what we are looking at here. So look at this equation right here. This shows a dicarbonyl compound, and it can form 3 different enolate ions, right? Because it's not symmetric, right? So we could form an enolate ion here, we could form an enolate ion here, and then we could also form an enolate ion here. And what's interesting here is it's not going to form the 7-membered ring, right? That's not favored. And the ketone attack here is also not favored, right? So we don't form any of this. So this is our major product. One of the ways that we know and we can make these not rules so much, but we can say, look, there's a trend where 7-membered rings aren't favored, is because people have done reactions like this. So they've started out with this and they've planned it really carefully. They've said, okay, look, I could get deprotonation here, I could get deprotonation here, right? And I could get deprotonation there, right? And so I'd form 3 enolate ions. Let's see which attack is the most favored. And then they analyze their products and they say, oh man, I almost didn't make any of that and I almost didn't make any of this. So it seems that the aldehyde attack is favored that forms a 5-membered ring. So that would be a part of research that organic chemists would do, would be to look at reactions like this and see what generalizations we can make about what types of molecules form.